Hi everyone, so today we are going to look at question 5. So let's take a look at the question first. So it mentions here that you have a progressive wave. Well, we are still in progressive wave, traveling wave, and this progressive wave is represented by the equation which is y equals to 0.5 sine 2 pi bracket t minus 2x close bracket. So as you can see, this equation is slightly different. After the sign, it's not a bracket straight away. Okay, usually it's sine bracket, then you have omega t minus kx. But here, they take out a 2 pi, then only they start bracket, then t minus 2x. So something interesting here. So we will try to look at what does this mean. Okay, so when we are given an equation, what we usually do is we compare it with the general formula to extract information about it. So y equals to 0.5 sine 2 pi t minus 2x. This is the equation given to us. But if we compare with the general formula, our general formula will look something like a sine bracket omega t minus kx, which we can't really compare because there's the bracket sign, it's different. Here you have a 2 pi factorized out, but for your general formula usually the 2 pi is inside. So what can you do is, maybe what you do is just take out the 2 pi then. So you can write a sine then 2 pi. So you try to mimic the shape of the equation that you are given. If they have a 2 pi factorized out, you do the same thing. But what should I fill in for this 2 part for the general equation? What should I put here and what should I put here? Well, you can think of it, it's actually quite simple thinking of it. Omega is equals to either 2 pi f or it can be equals to 2 pi over period. Okay, so since if you look at the question, they ask for something related to period, probably putting period will be a better idea. So if we factorize out the 2 pi, then what's left is 2 pi, then you have 1 over t inside the bracket. So you can change this question mark here and put it as 1 over big T, period. Okay, so we'll do the same thing for k. So what can we do for k here? You know, k is equals to 2 pi over lambda. So if you factorize out the 2 pi, what's left inside the bracket is 1 over lambda. So with that, we can change this question mark and put it as 1 over lambda. Well, now the thing seems better and you can probably do comparison more reasonably. So you can compare between 0.5 and a, and you can compare between this value in front of here and 1 over t, and you can compare 2 and 1 over lambda x. If you are not sure what am I meaning by this empty space, I should probably remove this equation and write it in the form which might be more understandable. So instead of writing t straight away, probably you can write it as 1t. 1t is the same as t, right? So 1t minus 2x. Now the shapes really, the structure is identical, so you can do a direct comparison. Then 1 will be equals to 1 over capital T, 1 over period, and 2 will be equals to 1 over lambda. Okay, so now we have structured the equation in the form which is appropriate. So let's try to solve the question. Okay, so the question asks for number 1, they ask for the wavelength. So if they ask for the wavelength, well, we have really straightforward information. 1 over lambda is equals to 2 per, now cm or per meter, per cm or per meter. This one, if they didn't tell you explicitly, probably what can you do is look through the question. If you look through the question, then probably you'll get some hint. Like for instance, around here, they say x is in the unit of meter. So most probably, because x is in the unit of meter, so if k is multiplied by x to form radian, so most probably k will be in the unit of per meter. So this will be in the unit of per meter. So if this is in the unit of per meter, then our lambda will be 1 over 2 and it will be 0.5 meter. Okay, so that's how you find the wavelength. Number 2, how do you find the period? Well, it's the same procedure again. 1 over period is equals to 1. This one is omega. You can call it radian per second. Oh, there's no radian already. You factorize out the 2 pi. So it's 1 per second. So big T will be equals to 1 over 1, which is essentially 1 second. So we can know from here that the period is 1 second and the wavelength is 0.5 meter. So we have finished answering question A. Moving on to question B. Question B requires us to draw a displacement time graph. Okay, for a particle at x equals to 0 and a particle at x equals to 0.25 meter. Let's take a look straight away at C also. C asks us to draw a displacement time distance graph. Okay, you can see the difference in the wording. For B, it's displacement time graph. For C, is displacement distance graph. Okay, so these are the two most commonly seen and most commonly sketched graph in chapter 10, but they are different things, so it's important that you are able to differentiate it. I discussed a little bit about it in the previous question, but just to be clear, let's do a bit of a rough intro to these two graphs here. So you have two types of graph. So one of it is displacement time graph and one of it is displacement distance graph. You usually call displacement time graph a YT graph, whereas for displacement distance graph, it's a YX graph. Okay, so these are different way of representing the wave, but they are not a complete representation of the wave. So okay, so a wave is a moving thing, right? As time passes, the wave moves because it's a progressive wave. But you are drawing your graph on a piece of paper, and a piece of paper has no play button inside it. So you cannot press play then let the wave move as time passes. So because it cannot move, so you cannot represent the whole wave in a single graph. You need to split it into two graphs. So these two graphs are a portion of the representation of the wave. So why do I say so? Let's look at it one by one. So displacement time graph, you can think of it as exactly the same as your SHM actually. Okay, it's related to SHM. So why is it related to SHM? If you notice here, they ask for the particle displacement time graph of the particle at x. Okay, so if you see here, what the first characteristic that you see is they give you the position already. So position is fixed. Why do they want to fix the position? Is because they want to lock, or they want to like specify. They want to specify the particle they want to investigate. Okay, I call it the particle of interest. They want to investigate what? For this particle, they want to investigate the SHM motion, because across the wave, along the wave, actually you can think of it as a series of particles. So by fixing a position, you are fixing the particle which is at that particular position. So you study the oscillation of that particle at that position, at that specific position x. Okay, you fix your x because you want to study the particle at that position x. What do you want to study? You want to study the simple harmonic motion of that particle at position x. How do you study? By drawing a displacement time graph, just like what you do in chapter 9. Okay, so you will predict that the shape will look something like y equals to a sine omega t plus phi or minus phi. Okay, so the shape will look similar to what you learned in chapter 9. If your lecturer teach you phi, then knowing this will be very helpful to plot graph here. Okay, then displacement distance graph. Displacement distance graph is a different kind of graph compared to displacement time graph. Okay, displacement distance graph, you can think of it as a snapshot. Okay, I would like to think of it as a snapshot. So if you take a picture of something, you are basically, the picture that you have taken, it's for a specific moment of time. Okay, your picture cannot move. It's not a Insta story or whatever. It's just a snapshot. So everything is stationary inside there because everything inside cannot move. That picture itself represents a single moment only. Okay, so that's why if you look at the question here, they will fix the time. If you look at the question, they fix the time. They give you the specific time because you are drawing the shape of the wave at a specific time. Okay, as time passes, the shape will change, right? Because the wave is traveling. But now you are drawing the shape of the wave for a specific moment. Okay, so for this one, the time is fixed. So what you are drawing is the shape of the wave. Okay, before that, in displacement time graph, you are drawing the simple harmonic motion. You are drawing how the oscillation of the particle. You are drawing the oscillation of the particle as time passes. You are drawing the oscillation of the particle as time passes. But for displacement distance graph, you are drawing the shape of the wave at a particular moment. Okay, time is fixed means by a specific moment. Okay, I hope this will help you to get a better idea between the difference between the displacement time graph and the displacement distance graph. So let's move on to solve question B. Question B asks for a displacement time graph, so we can probably label the axis of this graph first. Displacement is y, unit of meter. We assume everything is in meter because they never show anything with cm here. Then time graph means by here it should be time and second. Okay, so the first graph that they asked to draw is when the particle is at x equals to 0. So we are observing the SHM of the particle at the origin. X equals to 0 is the origin. So we are observing how the oscillation, how the displacement changes with time as for the particle at the origin. So this is similar to how you do it for chapter 9. So I can treat it as a bit of a revision. When x equals to 0 meter, your y, okay, what you do is you do a bit of substitution. 0.5 sine 2 pi t minus 2. Now for your x, you sub inside 0. So the answer that come out will be y equals to 0.5 sine 2 pi t. Well, this looks just like your, okay, I'm writing this as a reference. This looks just like your graph that you draw in chapter 9. X equals to a sine omega t. Okay, I'm just writing this as a reference. I should specify in your SHM. Okay, so how do we do this thing? We extract information first. First, we know our amplitude will be 0.5 meter. Then we know our omega will just be 2 pi radian per second. So since we know omega is 2 pi radian per second, it's useful for us to find the period because later we want to label it. Here is just 2 pi divided by omega. So the answer will be 2 pi divided by 2 pi 1 second. Okay, so knowing all these things, we can start to plot the graph. So I'll plot it in green. So first of all, see what kind of shape do we need to plot. There's no negative sign, so it's a positive thing. So we can draw the sine graph just as it is. No need to flip, no need to do anything. So usually what I think it's good is you can draw two complete oscillation. Okay, so you draw two complete oscillation, then what you do next is you label the specific position. This thing you need to label the amplitude, which is 0.5 meter. We only have to label for the opposite side as well. So it's negative 0.5. And what can you do after that is to label the period. So it might feel a bit incomplete, so if you want to label here 2 as well, that is good. So yes, that's how you draw a displacement time graph for the particle at x equals to 0. So this is how the particle at the origin oscillates as time passes. It starts from the equilibrium, goes to the highest point, drop to the lowest point, highest point, then drop to the lowest point, oscillate like this, just like what you see in chapter 9. So we move on to question B. Question B2 asks for the particle at x equals to 0.25 meter. So I'll need to move this over a little bit. 0.25 meter. Let me change a bit the layout of the stuff. Okay, so they ask for when x is equals to 0.25 meter. So now, if we write the equation down, let's write the equation down first. Let's don't rush. Y equals to 0.5 sine 2 pi then you have t minus 2x. X you sub in 0.25. So now if you multiply in everything, then it will be sine 2 pi t minus 0.5. Oh no, not 0.5, sorry. Minus pi. Okay, so 2 times 0.25 becomes 0.5. 0.5 times the 2 pi outside the bracket, it will just be pi. So you bring down the negative sign. So this is your equation. 0.5 sine 2 pi t minus pi. Well, if you compare again, it looks also similar to your SHM equation except that this time there's phi, and your phi is negative pi. You have a phase constant here. Okay, so to draw this kind of graph, there are many ways of drawing it. If you refer to YouTube, oh, there's plenty of video there. But what am I going to introduce you is based on a specific YouTube video that teach people how to draw trigonometry graph. The link is down in the description below. So I'll be drawing based on the technique introduced in the video. Okay, so feel free to refer that before you come back here. Okay, so the first thing I will do is, I will extract information just like just now. So the first information is A equals to 0.5 meter. No worries. Second information that I can extract is the omega is still equals to 2 pi radian per second. So what do I do with this omega? I change it to period, which is just equals to, we have calculated it just now, it's just equals to 1 second. So we extract the omega, we use omega to calculate the period. So the third thing I can extract from the equation is, well, the last thing, just the phase constant, phi. So the phase constant is equals to negative pi radian. Okay, there's a negative sign here, so you have to beware. So the phi is negative pi. Okay, if the phi is negative pi, what do I do with this phi? I'll calculate something called the phase shift. I call it P dot S, phase shift. So phase shift can be calculated using negative phi over omega. Basically, it's negative what's behind divided by what's in front. Okay, you can think of it like that, easier. Negative what's behind divided by what's in front. Okay, so if you calculate this thing, the answer that you obtain is negative pi divided by 2 pi. So your answer will be half. And if you check the unit, it will be second. So we extract three information. We extract amplitude, we leave it just as it is. We extract omega, we transform it into period. Then we extract the phi, but we transform it into phase shift. This phase shift represents how much we need to shift. So if we get half second, means by our graph needs to shift half second to the right. If it's negative half, then it shift half second to the left. Okay, just like we see last time in the previous question, you see a negative sign here. You see negative sign here means by the graph move to the right, right? So now you can see here, it says half seconds. Half second is positive, means by you shift to the right for half a second. Okay, if you're not clear, refer to the video link in the description. So the last step that I do is I combine these two values that I find, the period and the phase shift. I combine it to find what? That's the fourth step. I combine it to find the start and the end of my sketch. So I will start my sketch at T. I will start my sketch at T. T is 1 second. So I will just copy. Oh no, I will start my, I'll start my graph at the phase shift, because before that I start my graph at 0, right? Before I start my graph at 0. So now it tells me I need to shift half a second to the right. So means by I will start my graph at half a second. I will start my graph at half a second to the right of the origin. So my start is half a second. And where will I end? So I will draw it for one oscillation first. So one oscillation, you take one period, so plus t. So you end up with 3/2 seconds. So means by I will start my drawing somewhere around here. This is half, right? Then I'll end my drawing somewhere around here. 3/2. Okay, so what will I draw between this half and this 3/2? What will I draw in between this thing? I will draw the shape indicated by my equation. My equation say it's a sine, so I will draw a sine graph in between this start and the end. Okay, so let's do it. Between the start and the end, I will shift my graph so it will look something like this. So I will just draw a normal sine graph, but I draw it between the start and the end. Okay, so after I draw this, I extend the graph so that it goes back to the origin. Then I extend the graph so that it looks nicer. Well, that's it. This pink graph here is the graph when x is equal to 0.25. So it's better that we label it. This is when x is equals to 0.25 meter. Whereas down there, that one will be when x equals to 0 meter. Okay, so if you still cannot get it, never mind, we still have one more question. We still have question C over here. So we'll do the same thing for C. But the thing you should probably catch by now is there's 4 steps. You extract 3 information. The first one, the amplitude, leave it there. The omega, you transform to period. The phase constant, you transform to phase shift. By knowing phase shift, you know how much you shift from the origin. So you shift that much from the origin, therefore you start this far from the origin. Then you know you draw for one oscillation first. So the end will be one complete oscillation away from the start. So it's 3/2. So you pinpoint the position of the start and the end. Then you draw the shape indicated by your equation. If it's sine, then you draw a sine graph. If it's cos, then you draw a cos graph. If it's negative sign, then you draw a negative sign graph. Depends on the situation. Then you continue elongate this, extrapolate this graph to the correct place at the origin and the end, then you label the thing. So that's it. That's how you draw a graph with phase constant. Okay, so that's all for question B. We'll move on to question C. For question C, they ask for the displacement distance graph, and the two moment that they specify is when time equals to 0 and time equals to 0.25 second. Okay, it's in second. So let's move to the graph. Okay, remember one time is time equals to 0, the other one is when time is equals to 0.25. Okay, so let's label the graph first. You label, it's a displacement distance graph, so it's y for the y-axis, then it's x for the x-axis. Okay, after you label it, we have two questions to solve. The first one will be when time is equals to 0 second. So again, we copy down the equation from up there. So it's 0.5 sine 2 pi. Now for the time we sub in the 0, then we continue write down everything else, negative 2x. Okay, if you're not sure what I'm doing, I copy this equation, but now this one I don't interrupt it, I leave it as x, but the time I substitute in 0. And this is the result. Okay, so if you substitute everything already, then your result should be y should be equals to 0.5 sine, then you have negative 4 pi x. Okay, so when you see a negative sign here, I will recommend you to bring out this negative sign. So it becomes negative 0.5 sine 4 pi x. Actually, it's not that I recommend. It's a usual practice to bring it out. Okay, if you are not sure why can I bring it out, it comes from this thing. If sine is negative x is equals to negative sine x. Okay, it's one of the trigonometric identities that you learn in maths probably. Okay, this is only for sine. If it's cos negative x, it's just equals to cos x. You hilangkan, or you just drop the negative sign if it's a cosine. But if it's a sine, you bring out the negative sign. This is what you learn in maths. It's called trigo identities or something like that. I can't remember. Okay, so knowing this equation, we can start to plot the graph. Again, same thing, we extract the three information. A equals to 0.5 meter, first thing. Second thing is the K. The K here is equals to 4 pi per meter. Just now it was omega. But now if you see here, this is actually a y equals to a sine kx graph. Okay, what accompanies x should always be k. You won't have omega x, it's always kx. So what's happened in front of x is k. So k is equals to 4 pi per meter. Okay, so the third thing that you can extract is you can transform is lambda. Lambda transform from the wave number. So what you will end up with is 2 pi divided by 4 pi. So your lambda will be half meter. Okay, so you know these three things, start draw the graph. So if you observe carefully, the shape of the graph, it's a sine graph, but be careful, there's a negative sign in front here. So if you see a negative sign here, be very careful that your graph must be flipped vertically. So it's a negative sign graph. So always check the sign. That's why I asked you to bring out this negative sign out to the front, because it will change the shape of the graph. You flip the graph vertically. So now the graph should look something like this, a negative sign graph. As usual, I draw it for 2 complete oscillation. I think it's standard practice. Okay, 2 complete oscillation, then I label the stuff. First I label the amplitude. The amplitude is 0.5, and the other one, the opposite side, negative 0.5. Then for here, because it's a displacement distance graph, means this one complete oscillation here represents the wavelength, not representing the period. So you have to be careful of what you're labeling. So the lambda is half meter, so you can put here as half. So if here is half, then here should be 1. Well, I think that's it for your graph when t is equals to 0 seconds. So now let's move on to a bit complicated situation when t is equals to 0.25 second. Okay, if you cannot recall, t equals to 0.25 second from here. Okay, t equals to 0.25 second. So again, we do the same thing. We substitute this value into the equation. Y equals to 0.5 sine 2 pi. Then you substitute in the t, 0.25. Then you leave the kx as it is. Don't touch the x. You leave it as it is. So if you substitute in everything, it will be 0.5 sine, then this will be, there's a pi over 2, and there's negative 4 pi x. Okay, usually we put our phi at the back, so let's rearrange the equation a bit. So it will be 0.5 sine 4 pi x minus pi over 2. Oh, I bring out the negative sign to the front. Okay, if you notice, before this 4 pi x is negative, now it switched to become positive. Whereas pi over 2 before this is positive, now become negative. Because I bring out the negative to the front, because I want to stay consistent with this thing. I want the negative to be out at the front, so I just bring it out, so the negative become positive and the positive become negative, and I switch place because I want to make it look something like y equals to a sine, and again now you have kx, but now you have plus phi. Okay, so once you shift it to this shape, again you repeat the same steps. So if there's phase constant, 4 steps. First step, extract the first thing, which is your amplitude. Then you don't do anything with it. A equals to 0.5 meter. Second thing that you do, you extract the, before this is k, but now what's in front of x is just what is in front of x is the wave number. So we extract the wave number. K will be equals to 4 pi per meter. Then once you extract this, you change it to lambda. Last time it was omega changed to period, now it's wave number changed to wavelength. So 2 pi over k, it's 2 pi over 4 pi, then your answer will be half meter. So what you have done now is still the same as what you have done in the previous graph where t is equal to 0. So now the new thing is you have your phase constant. So phase constant, it's phi, then it's negative pi over 2 radian. Always remember to bring along the negative sign. If you see negative sign, bring along the negative sign, because we are comparing it with plus phi actually. Okay, so we continue. What do we get? What do we transform this phase constant to? We transform it into phase shift. Phase shift, how do you transform? By using this thing, negative phi. Before that is divided by omega. Now you divide it by k. But if you see it's still negative behind, divide by the front. Negative behind divided by the front. Okay, so it's still easy to remember. So if you transform, then what you are left is negative pi over 2 divided by k. K is 4 pi, and your answer will be 1 over 8. Your answer will be, up here this one is radian, down here is per meter, so your answer will be meter. So what does this mean is, for here, you have to shift to the right because it's 1 over 8. There's no negative, means by you start at 1 over 8 meter. Okay, 1 over 8 meter is here. So you start at 1 over 8 meter here. You shift this much to the right. Okay, so that's phase shift. So the last step, the fourth step, will be combining these two results that we get. Combine these two things to get what? To get where's our start and where's our end. Okay, the start will be just the phase shift. Okay, so for the start, you can just copy the phase shift over. So if you copy the phase shift, then your answer will be 1 over 8 meter. Then your end, because you draw it for one complete oscillation only, so it's from the start, you add on a length for one complete oscillation, wavelength. Then your answer will be 5/8 meter. So what does this mean is you will start your graph at 1/8. This is half. Half of half is 1/4. Half of 1/4 is 1/8. So it means by you will start here. 1/8. Then where you will end? You will end at 1 lambda away from 1/8, which is 5/8. So 1/2 is actually 4/8. So you move one more step, then here should be 5/8. So you label your start and your end point. After you label it, what do? You draw the shape of the sinusoidal curve inside the start and end. It's a negative sign. Negative sign. So we draw a negative sign graph. If you are not sure, it might be a bit confusing. So what you can do is you can plot a few more points in between. Okay, if you're not sure, then you know it will start somewhere here. Negative sign seems like it will go down, go up, come down. Okay, negative sign graph looks something like this. You can dot first, then only you start draw, no worries. Okay, so that's one complete oscillation. What can you do is you continue the front and the back, extend it, extrapolate it. So this one you can continue something like this. Okay, so that's it. That's how you draw the graph. If you feel a bit worried, why only label this few times only? Well, label everything if you want. So if that's 1/8, then here should be 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, 1. Okay, well, now you should be happy enough. All the time are labeled. All the position are labeled. So sorry, it's position, not time. Okay, so once we have labeled everything, we should actually write it clearly which one is what line. So the green one, this one I'll write, this one is representing when t is equals to 0 second, whereas the pink line is when t is equals to 0.25 second. So that's how you draw a graph when you have phase constant. Well, this is just phase constant, so it's still something related to what you learned in chapter 9. 4 steps: get the amplitude, do nothing with it, get the thing in front of x or the thing in front of t. If it's a yt graph, then it's an omega. If it's a yx graph, it's a k. Then transform it. If it's omega, transform to a period. If it's wave number, transform to the wavelength. Then you extract your phase constant. Then you use this phase constant to determine the phase shift. How do you determine phase shift? Negative phase constant divided by what's in front of your x or what's in front of your t, either a k or an omega. Calculate this. If it's a positive, means by you shift your graph, you shift from the origin for this much to the right. If it's a negative value, means by you shift from the origin this much to the left. Okay, just like your positive left, positive right, negative left thing. Okay, then after that, knowing this phase shift already, then you determine your starting point, which is just the phase shift, and your end point is your starting point plus the period or the wavelength. So you fix the point, then you draw the graph for one complete oscillation, then you extend, then you label, then that's it. Then you can finish draw a graph with phase constant. Well, it's a bit of a long video, so I guess stop here will be the good idea. That's all for this video. Thank you very much.